Welcome to the second video for Lecture 7. In this video, we will cover roots, poles, and zeros for transfer functions, characteristic equations, and some different forms that transfer functions can be written in. We will work with polynomial expressions which we can set equal to 0 and write in two forms. The first form as constants multiplied by s to multiple powers. The second form is written as the product of multiple s plus p terms. The p terms are called poles. The roots of the polynomial expression are the values of s, which make fs equal to 0. We usually use r to represent the roots, and r1 equals minus p1, r2 equals minus p2, and on and on. For many problems, we find the roots of a polynomial equation, and once we know the roots, we know the poles, because the poles are the negations of the roots. The bottom line is that the relation between a polynomial root and the equation poles is quite simple. We have mentioned transfer functions before, and we will talk about them again. Transfer functions are Laplace domain expressions that relate the input function in the denominator to the output function in the numerator. In a block diagram, the input function xs is transformed by the transfer function gs into the output function ys. This slide shows that transfer functions can be written in three different forms. Actually, the equations can be written in many different ways, but we need to be aware of these three forms. The first transfer function form is when the numerator and denominator are written as polynomials. This common form is used when we are trying to take the inverse using MATLAB and the residue function. The a's and b's are the polynomial coefficients, and m's and n's are the powers of s included in the equation. The expression should be written in a way that m, the highest power of the numerators, is less than n, which is the highest power of the denominator. If m is not less than n, then you must use polynomial division to remove some terms and produce a ratio term where m is less than n. You will rarely be doing polynomial division in this course. The second form is called the zero pole form. This form is related to the polynomial roots we have been using as part of the process to invert Laplace domain expressions using partial fractions. The p-values in the denominator are called the poles. The corresponding z-values in the numerator are called zeros. The zero pole expression can be equal to the polynomial form, for the zeros are equal to minus 1 times the roots of the numerator polynomial, and the poles are equal to minus 1 times the roots of the denominator. The k term in the zero pole equation is called the steady-state gain of the transfer function. We will talk more about gain later in the semester. Finally, the third form is called the time constant form. We talked about time constants briefly when talking about the fluid heater process. We will talk about time constants more later in the semester. This time constant form can be written if all of the roots of the polynomials in the numerator and denominator are real roots. Then the zero pole form can be modified into the time constant form. Tau a is equal to 1 over z1. Tau b is equal to 1 over z2. And tau 1 equals 1 over p1, and on and on. The k-tau term in the time constant form of the transfer function is the steady-state gain for the time constant form of the transfer function. At different points in this course, we will find it convenient to write the transfer functions in different forms. For now, just learn the terminology and the limitations. Both the pole zero form and the time constant form had k terms, which we called the steady-state gain terms. One way of thinking about the gain is to think about the transfer function as an amplifier, and the steady-state gain is how much the transfer function amplifies the input function to produce the output function. Many process control devices add some gain to the process. Remember that roots of a polynomial function are the values of s when a polynomial equation fs equals 0. Once we find the roots, we can write the expression in the zero pole form. Then We define the poles as the roots of the transfer function denominator times minus 1. Also, we define the zeros as the roots of the transfer function numerator times minus 1. It turns out that the values of the poles and zeros tell us a bit about how the transfer function will behave dynamically. At this point in the class, we will give two characteristics and observations about poles. Some of the comments related to final value theorem that will be talked about in the next video. If the poles of the characteristic equation of a transfer function are 0 and positive, which means the roots are 0 or negative, the final value theorem will apply to the transfer function and we can generally expect a stable process response. If the poles are 0 or repeated positive real values, this means that the denominator roots were 0 or repeated negative values. Again, the final value theorem will apply, and in this case, the process response will be expected to be stable but sluggish. When we say that a process is sluggish, it means that the process response will be slow and that it takes more time than we might like for the output to get close to the set point value. If the poles of a characteristic equation of a transfer function are negative real values, then the denominator roots are positive. This means that the final value theorem will not apply and the process response probably will not be stable. It also turns out that if poles are close to 0, then they will dominate the process response. In other words, that part of the expression will be more important than other terms. We haven't said much about zeros. At this point, all we will say is that zeros are the numerator roots times 0. They have less impact than the poles on the transfer function response. They do have some impact, but less than the poles. This brings us to the end of Lecture 7, Section 2 video about roots, poles, and zeros of transfer functions and the characteristic equation. Please write down any questions you might have and bring them into class. Thank you.